axis. If what you're used to looking at are the orbitals from chemistry, you're probably used to seeing pictures that look something like this. You have a blob over here, you have another blob over here. Or you have a blob over here and another blob over here, sort of along the x-axis or along the y-axis. You get these by combining superpositions of these two complex spherical harmonics. Essentially, what you do to construct the real spherical harmonics is to superpose the complex spherical harmonics. For instance, if I take this, which is e to the minus I phi, and this, which is e to the plus I phi, and I add them together, this is going to give me cosine phi plus I sine phi. This is going to give me cosine phi minus I sine phi, after I abuse the even and odd properties of cosine and sine. If I add these two together, for instance, I'll get cosine of phi plus I sine plus cosine minus I sine, and the I sine parts will cancel out, leaving me just with the cosine part. The cosine part, then, is going to be non-zero only along the x-axis, where phi is 0. If I combine them instead with the minus sign, I'll get the cosine parts to cancel out, and I'll end up with minus 2I sine phi. If you ignore the complex part by multiplying everything by I, for instance, you'll end up with just the sine of the angle, and you'll get something that's only non-zero along the y-axis. So you would get the same sort of two blobs that we saw when we looked at the case where m equals 0. So if you're seeing pictures with blobs off-axis like this, in the case where m is non-zero, you're looking at a chemist's interpretation of the spherical harmonics. We can keep going. I'm going to skip the case where NLM is 3, 0, 0, since you know what that's going to look like. It's going to have 3 concentric regions where this particle is likely to be found, and go straight to the case where L equals 1. This is m equals minus 1, m equals 0, and m equals 1. So once again, Roy G. Biv clockwise versus Roy G. Biv counterclockwise. For the case m equals 0, we don't have any complex exponential part, so we just have the plus or minus 1 sort of phase differences. We also don't have any azimuthal dependence, and our radial structure ends up having one radial node. So we're unlikely to find the particle at the origin. We're also unlikely to find the particle in this sort of spherical region here. And the angular regions where we're unlikely to find the particle depends on what spherical harmonic we're looking at. So in this case, we're unlikely to find the particle along the z-axis, and we're unlikely to find the particle at a particular radius. Same sort of picture for this one, except we're looking at azimuthal dependence in a different direction. Unlikely to be found on the z-axis, unlikely to be found at a particular radius. The picture for m equals 0 is that the particle is unlikely to be found on the xy plane and at a particular radius. So what I'm drawing down here is the structure of the nodes, the regions where the particle is unlikely to be found, since those are really the boundaries between the blobs in pictures like this. We can keep going higher still. This is if L equals 2 in the case of n equals 3. So the structures we get are slightly more complicated still. The case where m is as large as it can be here, this is m equals minus 2, m equals minus 1, m is 0, m is 1, and m is 2, always look the same. We have the particle unlikely to be found along the z-axis, and we have this sort of donut shape going around. If I draw my node pictures for this, my m is as big as it's going to get case is always going to look the same. It's unlikely to be found along the z-axis. If I draw my node pictures for this case, particle is unlikely to be found along the z-axis and unlikely to be found on the xy plane. So we have sort of two separate donut shapes. For the case m equals 0, the particle is unlikely to be found at two values of theta. So I'm going to draw two lines like this, and you'll have to keep in mind that these are representing cones rotated around in the xz plane. Essentially, there's a cone here and a cone down here where the particle is unlikely to be found. I'm going to erase that since it wasn't terribly instructive, but you get the idea. There are two angular nodes, two places in theta space where the particle is unlikely to be found. The same pictures, of course, apply over here and over here as they did here. Particle, in this case, unlikely to be found in the xy plane and unlikely to be found along the z-axis. This particle being unlikely to be found on the xy plane really refers to a node in theta where the the spherical harmonic evaluated at theta equals pi over 2, rotating 90 degrees down from the z-axis, is 0. So that defines the xy plane. Similarly, of course, over here, particle is unlikely to be found at theta equals 0 or theta equals pi along the z-axis. So these are the sorts of structures that we get from spherical harmonics. If you make superpositions of these, the way the chemists like to, you need to keep in mind now that notice we have 2 points along the m equals minus 2 and m equals plus 2 where the color is red. That's because we're looking here at something like e to the 2i phi minus 2i phi in this case, and e to the 2i phi in this case. And when I superpose those, I'll end up with sine 2 theta or cosine of 2 theta. So I'll end up with pairs of blobs. If I draw that out in 3 dimensions, you'd end up with blob, 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 blob. Versus, in this case, the same sort of thing, but rotated 90 degrees. So sort of blobs on axis versus blobs off axis. It's very hard to tell given these tiny sketches. So I suggest you go and look at pictures from the chemist's perspective if you're curious. You probably have a chemistry textbook or can find pictures online quite easily. As before, in physics, we're not afraid of complex numbers, and we end up with these sort of circular shapes for the non-zero values of m in our spherical harmonics. From the chemistry perspective, I'm going to go back through these slides again. These spherical orbitals are called s orbitals. The L equals 1 orbitals here, where we have these blobs, or in our case, donuts, the blobs of the chemist's approach, are called p orbitals. And the case where L equals 2, we have the slightly more complicated structures. These are called d orbitals. The origin of those names comes from a really antique spectroscopic convention, where the spectral lines that are emitted by an element are named according to their structure. Sharp for s orbitals, principal for p orbitals, diffuse for d orbitals. We now know that that doesn't really have a lot of comparison or relevance to the actual structure of the orbitals, but the names have stuck. To check your understanding of what the hydrogen atom orbitals look like, here are a couple of things that you can try using the simulations at Falstad.com. He has a hydrogen atom orbital visualization tool, and you can use it to make complex combinations. So there are some specific things that you need to do in order to answer these questions on those simulations, but I encourage you to play with this simulation and try and get a feel for what the orbitals look like, both from the chemist's perspective. Those are real real hydrogen atom orbitals, as opposed to the physicist's approach, which is the complex approach. So the specific sub-tool of this visualization that I'm suggesting you use here to answer these questions is complex combinations of orbitals with n equals 1 through 4. But you can look at the real orbitals as well and make combinations of the real orbitals as well. So that's about all I need you to understand about the appearance of hydrogen atom wave functions. These things are, of course, very important from the perspective of chemistry, but from the perspective of physics, it's really just these complex wave functions, which have a variety of quantum numbers and a variety of geometrical representations, a variety of geometrical structures.